Hello, and welcome to Physics 2212 Lab 5, which uses a falling magnet and a solenoid to represent Faraday's law. The purpose of this lab is to use Faraday's law to relate the magnetic field of a falling bar magnet with respect to time to a Curly electric field around an aluminum solenoid, which can produce a current. We will see that this current can then produce a magnetic field which exerts a force on the source of the external magnetic field in accordance to Newton's third law. To do this, we dropped a bar magnet through the center of a roll of aluminum foil acting as a solenoid and recorded the time it took to fall all the way through the solenoid. This was then repeated with the bar magnet the opposite direction, and then by just dropping the bar magnet the same distance in plain air. I then created a computational model of this occurrence using VPython, which I then compared to my experimental data and found that the magnet in my computational model took about 3 times as long to fall through the tube than the real-life magnet took. Some important concepts in relation to this lab are first Faraday's law, which states that when the magnetic flux linking a circuit changes, an electromotive force is induced in the current proportional to the rate of change of the flux linkage. We'll see this in the computational model in the code that I used to write that. The second is Newton's third law, which states that the force of an object exerts on another object is equal and opposite to the force that the latter object exerts on the former object. Another important concept would be Newton's second law, which states that the acceleration of an object is dependent on 2 variables, the net force acting upon the object and the mass of the object. Those, along with the Biot-Savart law, which describes the magnetic field created by a current-carrying wire, as seen in this equation, which will relate to our model, will all be seen in my computational model. Here you can see we have the experimental data. I did 10 trials for each method, the first being the north end of the magnet falling first, the second being the south end of the magnet falling first, and then the last being the magnet falling through plain air the same distance as the solenoid. All of these times are taken in seconds. Here we have a video of us completing this experiment. Here is the final results from my computational model, along with just a little glimpse at how I calculated the change in flux over the change in time, using the various initial conditions and other equations. To complete my computational model, I first set up the initial conditions that I used in my experimental model. I then calculated the magnetic field at the position R relative to the magnet, which then I found the change in flux over change in time, as seen here on the right, through each ring from the falling magnet. I then used Faraday's law to calculate the induced current in the solenoid. I then used the Biot-Savart law to calculate the force exerted on each of the current-carrying rings. I then used Newton's third law to calculate the force exerted on the falling magnet by the current-carrying rings. And then I calculated the net force, and finally I used Newton's second law to calculate the velocity and position of the bar, which I used to create this velocity versus time graph, along with showing how the magnet fell through the tube. There are many important conclusions that come from this lab. One being that the coloring that was seen in the previous slide, the red coloring, indicates the magnitude of the current flowing through each ring. Red indicates the current flowing in the clockwise direction, while blue would indicate the current flowing in the counterclockwise direction. My computational model showed only clockwise, as viewed from above. And this is because that the current through the tube that was induced is only running clockwise. The second conclusion is that when I flip the magnet around, the dynamics don't really change, but the magnitude of the charges does change. So the magnitude of the magnetic force changes, which we can see in my experimental data as while the north side of the magnet is on top falling, the magnet took longer to fall, which would be due to a stronger net magnetic attraction between the magnet and the tube. And my total in-time tube of my railroad system was about 1/3 as long as my computational system, which after some fiddling with my code, I found that that could be due to the magnitude of mu, which I took from my third lab, which was 1.53. I found that when I decreased that to 0.81, then my time in tube was equal to that of my real life system. I also found that the shape of the velocity versus time plot, because it's so consistent, as seen in my previous slide, that tells me that I can assume that the net forces are equal to 0. I then looked to find if the resistivity of the conductor was reduced as close to 0 as possible, how the dynamics would change. And I found that the time in tube when the resistivity is near 0 is greatly increased. I believe it was about like 8 or 9 seconds versus the 3 seconds in my computational model. I also would assume that cutting holes or slots into the tube would affect the currents, because there would be less magnetic force from the rings because the area of the rings would be much smaller if there were holes cut into it. Thank you so much for watching my presentation. If you have any questions, please send them to my email here. Thank you.